All right, hello all, and welcome to the Introduction to Programming Languages talk for the CS Club at Mesa Community College. This is just a video of the presentation I gave earlier this day, not April 4th, but September 19th. So here we go. So what is this talk about? There are many languages out there, each with some unique thing about it, mainly to do with the core of the language, but there's stuff outside of that that we'll also talk about. In a sense, this talk is somewhat a zoology of programming languages. If you find these topics interesting, you might actually like computer science as a major. Classes to look forward to are CSC 240, which is programming languages at MesaCC. So that includes C, C++, I believe Scheme or Racket, and then Prolog. And then for those transferring to ASU, the closest college nearby, you could look forward to CSE 340, which is Principles of Programming Languages, which takes the concepts from this class and expands them into the more theory, digging deeper into what makes those programming languages unique. CSC 355, which is Introduction to Theoretical Computer Science, and then CSE 440, which is Compiler Construction 1. So on this page, which I'll zoom out a little bit, I had a whole bunch of different programming languages and their mascots. I'll try to do it from memory real quick. We got Ferris the crab, which is the mascot for the Rust programming language. C++, Haskell, not to be confused with Pascal. So this is Haskell, not Pascal. MySQL, and the dolphin's name is Sakila. Python, Lua, this is Erlang, Java, JavaScript, Julia, R. This is the Zig programming language, and it has two mascots. This is Ziggy and this is Zero, and these are called Ziguanas, not iguanas. This is Go, and this is the Go Gopher. So Go actually has a logo which is just GO in this same teal color, and then it's tilted slightly. This is Gleam, and the mascot is named Lucy. This is Raku, which started as Perl 6, and this is Camellia, the butterfly. This is the Lisp alien, and I believe this is specifically for Common Lisp, but I could be wrong. This is MATLAB. This is OCaml. These are actually the same programming language. This is Perl 1 through 5. 5 is the latest version. Likewise with this. The reason they have two different logos is because one of the most popular books had from O'Reilly had a camel on it, so it kind of took precedence in the community. And then this is a Perl onion. This is Ruby. This is Rock, R-O-C, so no K. This is not a programming language specifically, but it's SWI, SWI, Prolog, so it's like the specific compiler, you could think about it, or interpreter. And then this is not a programming language, it's a kind of a trick on here. Most people know ASM as the assembly languages, but assembly is not a language, but a family of languages, and this ASM has nothing to do with any specific one. One thing to note is that Lisp is also kind of the same, so this Lisp alien I believe is specifically for Common Lisp, but it might be a mascot for the whole Lisp family of languages, so that includes Scheme, Racket, Common Lisp, and all of the other descendants. One thing to note is that Java is not JavaScript and JavaScript is not Java, although the naming conventions are kind of there to piggyback off of one another. I circled Julia, Python, and R because if you've ever heard of Jupyter Notebooks, that comes from the JU in Julia, the PYT in Python, and the R in R, so Jupyter. So kind of interesting. Python is named after Monty Python, and then let's see, did I have anything else on here? Prolog stands for programmable logic, and I think that's it. So what is a programming language? There are nuances on this, but a programming language is, in this talk, will be anything that's Turing complete. So when something is Turing complete, if A is Turing complete and B is Turing complete, they could technically do the same things, but I'll talk more about that on the next page. So things in this talk, HTML, CSS, Markdown, and the like, will not be really considered so much in this talk because they don't have control flow or logic. They're still a computer language and they're ubiquitous, but you're not really thinking like, oh, should I use HTML over something else? Well, yeah, you're probably going to use HTML if you're doing web design, and same with CSS. There's not really a choice. There are plenty of markdowns, but they're not interesting to talk about in the same way that programming languages that are Turing complete are. But what really is a programming language? Well, this is also nuanced too because of the various stuff in this talk. A programming language is anything where you could take your thoughts to do something, and it is the interface that lets you translate those thoughts into machine code. So as long as a CPU could do it, hopefully the programming language gives you the tools to translate your thoughts into that. Crafting Interpreters is an intro book that is free online, which I have right here, and it's just craftinginterpreters.com. And if you scroll, so this is what you could see what they're talking about. So source code scanning, tokens parsing, abstract syntax trees, optimization, all of that stuff. All of that goes into making a programming language. But if you go down to the web part, you could hit read now and see all of this stuff. You do make the programming language in here twice. You make it once in Java, which is part 1, and once in C, which is in part 3. That gives you kind of various stuff to look about. So let me go back a few pages. That's something you might talk about in a compiler class, in a compiler class, or a theory of programming language type class. What makes a language specifically, like how you type it and all of that, has to do with the language spec. So usually these are written out and you can read them online. So that could be the documentation that specifically tells you what every single thing in the language does. So this could be the data types, this could be special built-in functions, so on and so forth. And many times this is written in BNF form, notation, or Bacchus noir form. So let me actually just show you what that looks like. Oops, opened up in a new tab. So normally you would have a symbol on the left side and then what that symbol does on the right. So what that could be is you could have like a plus sign here and the appropriate kind of assembly or such on this side that this symbol will interpolate. But it would be something like A plus B. So there's a lot that goes into that. They have an example here of what a file for postal stuff would be looked at. So you would have to have the address, and an address is named. An address is made up of a name, street address, and zip. But a name is part of a personal part. So that's your first name in English-speaking countries. Last name. Suffixes, technically there could be a prefix, but they don't have that on here, and so on and so forth. So this is kind of like the most abstract part, and then each of these are broken down, and that's what BNF form does. So let me close that and get back here. And yeah, that's what a programming language is. So a programming language is just that interface between your thoughts and the machine code. Here's a brief history. So 1849, Ada Lovelace publishes the first computer program, which is really just an algorithm, and it was for Charles Babbage's mechanical computer that could do some kind of simple math. In 1936, Alan Turing invents the A machine, which his PhD advisor, Alonzo Church, later calls a Turing machine. So let's see if there's a kind of a representation of that. What it is, it's an infinite strip of paper that's read into a machine, and it kind of just executes the possible instructions that are on the tape. And the tape technically can be infinitely long. If you've ever heard of the halting problem, it has to do with Turing machines. But kind of interesting, this if you've heard of finite state machines, also something to do with this, but there should only be a finite set of instructions or an alphabet that could be recursively used to make any size program, and the Turing machine is what you could use to run that set of instructions. 1947, a book comes out called Programming for ARC, which is I believe a CPU, and it showcases kind of the first assembly language in print. 1952, Grace Hopper, who this is like the main character in Hidden Figures, her team coins the term compiler and then creates one for a language called A0, which will later influence a language called Flowmatic, which later influences COBOL. So at the beginning of the pandemic, some people weren't getting stimulus checks because the language that did that was in COBOL. So they had to hire people that had expertise in this, because now it's not such a used language. But it was kind of like one of the first compiled languages that a lot of people were learning. And it has to do with common business logic, I believe is what it stands for. So it's for people that weren't really great at programming, but kind of knew what they wanted to do. 1954, John Backus and team start writing Fortran, which is an extremely popular language and was kind of used to speed up writing math. John Backus is also the person in Backus Noir form. 1958, John McCarthy designs Lisp for artificial intelligence and research and symbolic calculation. Fun fact, AI was supposed to just be a summer-long project where grad students at MIT were just supposed to solve basically everything you could do with artificial intelligence, and that was back in 1958. So we are obviously still having major breakthroughs to this day, and there have been a lot of AI winters since 1958. 1963, Dennis Ritchie and Ken Thompson. So I talked about these guys in my operating systems video. They made Unix. But before that, they created the C language, one of the most influential languages, and probably the language that most other languages are written in. 1972, Prolog is designed by this team, and it's the first programming logic programming language. I took a philosophy class at Arizona State University called Philosophy of Artificial Intelligence and Computing. I believe it's Philosophy 314, and we read Kowalski's book. It's pretty fascinating, and we had to use Prolog for that. 1972, Smalltalk is invented, and this is the first object-oriented programming language, which will later go on to influence things like Java. 1973, Robert Milner invents ML, which in this case stands for meta-language, not machine learning or machine language. He invents this in Lisp, which will influence nearly all functional programming languages moving forward. 1978, IBM releases the first commercially available SQL, which uses relational algebras to search databases. So a relational algebra, you could really think of that as a Venn diagram. 1980, something called C with classes is invented by Bjorn Stroustrup, and this is better known today as C++ when the name was changed. And this, there's many reasons to think C++ is amazing and it's very influential, but one thing it does that I think is unique is it inspires aggressive compiler optimizations, which will later go on to influence things like Rust and other Carbon and languages like that. 1987, Perl is created by Larry Wall, which is kind of the glue of the internet. If you download Git on a Linux machine, you will also pull down dependencies that are Perl related because Perl is part of Git. In 1990, Haskell is introduced, and it introduces type classes and special things you could do with types. This inspires usage of abstract mathematics, so things like category theory and abstract algebra, to leverage type safety. In 1991, the first public release of Python is introduced, Python 0.9 by Guido van Rossum, the language creator. 1995, James Gosling creates Java, which influenced the mindset of write once, run anywhere, because Java is ran in a virtual machine, the JVM, which is the Java virtual machine, and the compiler compiles to Java bytecode, so your computer can't directly read Java bytecode. It has to be run on the JVM and the output sent to the terminal or a window. Again, in 1995, Brendan Eich develops JavaScript in 10 days, and some people are suffering the consequences of that planned project. But it does also allow for some weird things to happen, which makes the web kind of beautiful like it is today. Beautiful in a lot of weird and quirky ways, so it's kind of a lovable quirkiness. 1996, Objective Camel, which later becomes OCaml, is released. And this is kind of one of the first times that functional, imperative, and object-oriented programming comes together in one package. In 2003, Chris Latner and Vikram Adve released LLVM, which this is not a programming language, but it's a toolchain and compiler set that makes compiling to different CPUs easy. In 2009, Ken Thompson, Rob Pike, and Robert Greismer invent Go. Sometimes it's written as Golang because of the website name. And this, at a systems level, makes concurrency and networking kind of easy. In 2015, Rust is released by the Mozilla Foundation and inspires new programming languages and alternatives to either garbage collection or malloc or memory allocation. So this is the birth of the cult of Rust. And I say that because there are some people in the Rust community that have the philosophy that everything should be rewritten in Rust. And the United States government just came out with something called either Tractor, or in my mind it makes more sense to call it Tactor, which is the translation of all C code to Rust code. So there is a big push to translate all C programs into Rust because of its memory safety features. So one thing I think that is really important when talking about different programming languages and what I think makes them very unique is their paradigms. So before I get into paradigms, I just want to make a note of this note at the bottom, which I'll make a little bit bigger. One thing when I first gave this talk is I talked about Turing completeness, which I did say earlier in here that anything that's Turing complete, if A and B are both Turing complete, then they could technically do the same things. So in all of these languages, even though they have different ways of thinking and programming, that technically doesn't matter because you could write the same program in any one of these paradigms. And many new languages are what are called multi-paradigms. So they things like Rust and OCaml actually take stuff from some of these or all of these and kind of package them all up. However, that doesn't mean writing a language in one language is idiomatic, which means the standard way to write it or using common phrases. So if you had to write a C program that would do something simple in Prolog, that would probably be very difficult, and likewise vice versa, because the way you have to think in either of those languages are radically different from one another. So let's go over the paradigm. So there's procedural, which is kind of like just writing a recipe. So it's step-by-step instructions. There's object-oriented, which has a lot of similar features to procedural, but now you have these things called objects, which you could kind of think like templates or abstract classes that you could have both attributes and functions within. So now things could talk to each other through just the objects versus everything being declared in the file and everything being able to talk to each other. So that has to do with something called encapsulation and privacy versus public stuff within a class. There's functional programming, which gets its name from math functions. So these languages kind of encourage doing function composition, which if you've ever taken an algebra class, that's like the FOG, which is the function composition. And then finally, we got logical, which there's not a lot of different types of logical languages, but Prolog is programmable logic. And this paradigm is very radically different than the others because what you do is you set up facts and relationship between those facts, and then you kind of interrogate the interpreter to ask it questions and see if the database knows anything about the things you're asking it about. One thing to note is that I have single asterisks on this and double asterisk on these. That has to do with something called imperative programming, which these two are, which is kind of that give a set of instructions and let it run through each instruction, and telling the computer how to do each of those steps, versus these two, which are normally what are called declarative. And that's where you kind of tell the computer what you want and it kind of figures it out. Now, everything under the hood is technically imperative. It's language features that abstract that imperativeness out to make it declarative. So C theoretically could be written in a way that is declarative if you write a whole bunch of functions and then ship those functions out as a library. You're abstracting the actual step-by-step part and just giving it the declarative names. And likewise, you could kind of do that with these two in the opposite way. But let's look at some examples so you know what I'm talking about. So here's an example in C. So I declare a function at the top of the file so that I could call it later. And this function is called square, and it takes in an int, just a single int, and returns that int multiplied by itself, so squaring the number. I then call the include file so that I could have printf, and this preprocessor macro pulls in the library and pastes it into the program when I compile it. All languages all programs for C technically start at a main function, so I have to declare that function. And then I call the square function and store it in a variable called x. And then I print it out so you could see the result of that here. And then I return with an exit successful to tell the computer that I'm done running this program. Now, if I had written this part down here, the compiler wouldn't know what I'm talking about when I got to this step, because square has to be defined earlier in the file for it to quote unquote exist. I cannot have this below, because then when I get to this step, the compiler won't know what I'm talking about when I say to square 9. So everything's listed out in order, and I have to define functions before I call them. Here's an example of OOP, or object-oriented programming, in Python. So what I'm doing is I'm creating a class called parrot, and I want parrots to have two attributes here, a name and an age. So this doesn't mean I have any parrots in my program yet. What I have to do is instantiate or make an instance of a parrot. So parrot 1, I'm making a new parrot, and I'm going to give parrot 1 the name of Blue, and then parrot 1 the age of 10. I then do that a second time here and then print out the results. So here you could see that I do have this object here called a parrot, and then I'm assigning that class that has a whole bunch of attributes in it, different values. Now, this could technically be done in C, but it's when I start adding methods here or functions inside of the class that C can't do that directly in the same way. So in C, there's something called structs, which a struct could have simple variables, but it can't have any functions inside of it. And that's what makes OOP powerful, because if I wanted to make a function called squawk here for parrots, I could do that, and then say a dog class could not call the squawk function because the squawk function would only be in a parrot class, whereas a dog function might have something like the dog class might have something like bark as a function. And it's nice to have those encapsulated within those objects, and that's what makes OOP powerful and something that a procedural language could not do. But notice how I wrote out the instructions step by step in both of these. That doesn't necessarily change here, although Haskell is a language that's what's called lazy. So even if I wrote all these things into a file, I don't have to necessarily run them in the specific order. I could call them at different times to where some of the code might never be ran depending on what I'm asking when I'm running the program. But this is a functional example. So anytime you see brackets, that's what generates a list of numbers. And if you've ever done set notation, this should be really familiar to you. So basically, I want a set such that the elements of that set come from a list of 1.10. So in Haskell is an extremely smart language where if I gave a pattern here that's kind of recognizable, it will generate a list based off that pattern. So I could have given it the even numbers if I did 2, 4, 6, ... up to like 1,000. It would generate that list of even numbers between 2 and 1,000. Here, just going 1.10 will generate the list 1 through 10. I could have technically just written this, but sometimes it's nice to store it in a variable, which is what this notation would do. On the same line, I'm saying give me a set where those sets where the elements of the set are from 1 to 10, but I only want the even numbers. So notice here, I didn't define what even is. Haskell just knows what even numbers are because of things that are baked into the language. So this set is the same as this set, except only the even numbers. So I've essentially cut my list in half to have to filter only what I want. Now we're going to use that idea of function composition. So I'm going to do the same thing, but now I'm going to slap on that I want all of those numbers to be negative. So this is negating all the numbers in that list. And then finally, this is kind of interesting. So I keep stacking stuff on top of this list for function composition. But in this part, I'm not getting a smaller set than I had before, or the same set but just doubled, which is what I'm doing here. I'm multiplying everything by 2, but I actually doubled the list size. And the reason for that is that I did not write the function mappings in the right order. So what I thought this was going to do was double this list. So I thought I was going to get -4, -8, -12, -16, -20 down here. But you can see I have -2, 4, 6, 8, so on and so forth. And the reason that is because even though I'm asking for the even numbers of this list, this 2 times function is getting applied before the even function takes place. And since functions are not commutative with one another, this took precedence, so it actually doubled every number in here first. And when you double or when you multiply by 2 a number, it automatically becomes even. So this even x right here is actually pointless. I could take it out of this line and I would get this same exact number here. What I should have done is swap these, so I'd have even out here and then map 2 times out here, and that would have given me this list doubled. But I wasn't thinking at the time, and that's why I think paradigms are so important. Because if you're not thinking the way the language wants you to think, sometimes you can make these mistakes. So this is a really good example of that, why thinking the way your language wants is important. So here's a logic example. In this slideshow format, I can't show Prolog, but I could show you it running on my computer. So I have a file here called Socrates, and then Prolog files end in PL. So let's open that file. So anytime you see this symbol, that means there's a relation. And if you don't see that symbol, that means it's a fact. So here I'm declaring that there is something in my knowledge base called Socrates, and Socrates has like the man characteristic, or is a man. Likewise, down here I have something called Zeus, and Zeus is a god. Now the way you would read this line is kind of backwards from the way you would say it. You would say, if something is a man, then it is mortal. Likewise down here, if something is a god, then it's immortal. And then here, if it's a man, then it's living, and likewise with a god. And you do have to put these on 2 separate lines so that Prolog knows what you're talking about. But let's run it with the SWI Prolog engine. So let's run this. So the way you work with Prolog is that you declare those facts and then you ask it questions by using a capital X as a kind of a question mark. So what we're doing here is we're asking Prolog, hey, is there anything that's a man in this database? And it says Socrates is a man. Let's say though I wanted to ask if there's anything that's a woman in the database. Nope. Nothing in this knowledge base is a woman. Let's go with God. And you do have to end your statements with a period. So there is a god in our database named Zeus. So those should be obvious because I declared those facts instantly. But if I ask, is there anything that is immortal in my program? It says Socrates. Well, at no point did I say Socrates was a mortal, but I gave it that relationship that anything that is a man is mortal. So you could expect that that happens also with a god. But if I do living, if I ask Prolog, is there anything living in my database or knowledge base? It's going to say X equals Socrates, but notice I'm on the same line. That means Prolog still has something to say. So you could continue either with enter, or you could do the semicolon. And it tells us that Zeus is also something that's living. So really interesting. I'm going to come out of SWI Prolog, and then I'm going to show a paper I wrote for my philosophy class in artificial intelligence. So let me go up here. So this is about natural language processing in Prolog. So in English language, sentences are made up of noun phrases and verb phrases, and then we have to define what all of those things mean. So this is kind of like the Bacchus-Knorr form. I have something complicated up here, and then I keep breaking down what that means. So a noun phrase has a determinant and a noun. A verb phrase has a verb and a noun phrase, or a verb phrase could just have a verb. And then I define the possible determinants, nouns, and verbs in my sentence. So this is kind of what the syntax tree could look like. This is a specific syntax tree. And then this was the file that I wrote. Not super important, but you could see I asked the interpreter, is a good man is hard to find. Is that a sentence within my system? Well, I don't have the word hard in here, and I don't have the word find in this syntax tree, so obviously that's not going to be a sentence. But I could add all this extra stuff with adverbs and prepositional phrases and stuff like that, and then build up the phrase to make it so that's true. So prologue, very different than the other ones. Still Turing complete though. So yeah, that's prologue and logical programming. Very different, very cool. So I think paradigms are the most important thing to think about, because thinking in the language is the quickest way to getting your idea done, but there are a lot of other important reasons to choose one language over the other. You could talk about high versus low level. So one thing I like to talk about is you wouldn't want to make a pacemaker in Python because people would probably die. The reason for that is because Python doesn't have a lot of great ways to check about overflow, underflow, and stuff like that. It doesn't give you direct access to memory, so a pacemaker would have to have probably not a lot of RAM and low CPU power or whatever it runs. So you would want to have something that you could get as close to that bare metal of the pacemaker as possible. So that's why you would want a low-level language versus a high-level language. Low-level meaning low or close to the hardware. High meaning more abstracted away from the details. Static versus dynamically typed. So statically typed means that you have to declare the type of the variable. So that could be integers, booleans, characters, stuff like that. In a dynamically typed language, that doesn't matter. You could switch the types on the fly. We'll look at examples of that and talk about why those would be pros versus cons. Compiled versus interpreted has a lot to do with high versus low, but compiled languages are normally significantly faster when running many instructions versus interpreted languages. Not always the case. You could write bad code that makes the compiled language slow, but normally it's very fast because there's compiler optimizations to make the machine code run it as efficiently as possible. So this would be like your C languages, and this would be like your Python languages. Direct access to memory versus garbage collection. So this could have just been called memory management versus garbage collection. Languages like Java have a garbage collection feature, which means that when you declare new objects or new arrays or anything like that, the Java compiler is kind of doing all of that for you, and the JVM is accessing those memories and any which way it sees most efficient. That does not work the same way in memory managed languages like C. In C, you have to call functions like malloc, which is memory allocation, to get new structs or anything like that onto the heap. So there's heap versus stack memory, and garbage collection, things are kind of done for you, and memory managed language, you do everything yourself. This could lead to faster code, but it's also very dangerous because there's a lot of ways to shoot yourself in the foot when you're doing your own management. One of the biggest one is memory leaks, which that happens when you're not careful about freeing the memory when you're done. Some people care about active development and standardization. So in languages that are currently being actively developed on are kind of nice because you're getting new features. So C++ every so many years comes out with a new version, which just adds new features, and people really like that. One thing I know that's being talked about in C++ is something called reflections. I don't really understand the detail, but I know it's something a lot of people talk about in the C++ community as being a possibility. Now, sometimes this is not a good thing because you have the transition from a major version like say Python 2 to Python 3, which has some backwards compatibility but breaks other things. So a lot of people were upset when Python released Python 3 because it unsupported all the stuff they were doing in Python 2, and they basically had to rewrite their code to fit the Python 3 standards. So sometimes that's not always a good thing to be in active development, but most people like that stability and the fact that the creators are still trying to do stuff to improve the language. One example that is kind of within this realm is Zig is a programming language that I believe is currently on 0.13 as the version, and some people don't want to use Zig purely because it doesn't have a 1.0 or greater release. So they just don't believe that the language is stable enough, which in some ways is kind of true. But companies like Uber are already using Zig in their production code base. So it's clearly working for huge companies, but other people just don't want to take that risk to write code and then that code becomes obsolete or unusable when the language changes at the 1.0 level. Some people care about other unique features like compiler options or Unicode support or different commands or built-in libraries. Which kind of goes with package managers down here. And the reason this is in italics is because package managers, if you listen to the operating system talk, doesn't necessarily mean the same thing as the package manager for a language. They actually do the same thing, it's just the scope of them. Something like Arch Linux has the Pacman package manager, which actually could download packages for other languages. So on the flip side, you have something like Python, which has the pip. Pip is a way to download packages. You could download pip packages with your Linux package manager. And there's various reasons for doing that and not doing that. But some people care about package managers because it makes things easy on them. Languages like C and C++ do not have package managers as far as I'm aware. There might be some out there, but they're not very popular and not recommended as far as I know. Rust has Cargo, and Cargo is really good at downloading packages. Haskell has something called Stackage, and also Cabal. Different philosophies, but they download packages for you. So a lot of people really like these features in languages, and that might be a reason to choose them. And then the last category I have here are oddities. And this one's kind of weird, but I'll show you an example of what I mean later with a C kind of gotcha. So oddly enough, which I didn't talk about being a general purpose language, that has to do with paradigms. So there's kind of two different philosophies for programming language. There's general purpose languages, which are almost everything you know, and then domain specific languages. So that could be like GameMaker script, which is only used to make games. You wouldn't be using GameMaker script to write anything outside of a game. Most languages are general purpose that you know of. There are probably more domain-specific languages. It's just that if you're not in that domain, you would not know about them. Almost everything described here doesn't matter because people out there have either remade popular languages to have the features above, or they forked the language, or many other things. Cython is Python that is compiled into C. And then there are interpreted C interpreters, I guess. But you wouldn't really use these unless you know exactly what you're doing, because the people that are making these kinds of things know exactly what they want and how to use them. So there's probably not a lot of documentation or tutorials on how to use them. So, and you're breaking the idiomatic way, which normally you don't want to do. You don't want to force a square peg into a round hole. Some people do, and they have successful results, but that's probably not what you want to do. You just want to get your idea done in the most efficient way possible. And then another example is TypeScript is JavaScript with static types, because Java is a dynamic language, or JavaScript is a dynamic language. So here is an example in Go. Oops, let me zoom just a little bit out. So Go is a static language. So what we're doing here is we're importing two libraries, the format function, which will allow us to print, and then complex numbers in the math library. One nice thing about Go is that in Go, you have the variable name on the left and then the type on the right. Contrast that with C, which has the type on the left and the name on the right. And what we're doing here is we have a variable called to_be, and that's a Boolean type that we assign false. Then we have the maximum integer, which this is kind of a bad naming scheme because we have a unsigned integer 64-bit, so this should really be called maxint64, but that's all right. And this is how you would get that number. And then Z is normally the variable used for complex numbers, so this is a complex 128-bit character. And then they're doing this complex square root on here. And then in our main function, we're just printing the type of the variable and the value of the variable of each of these things. So we got these down here. So obviously the Boolean was false. That one's kind of straightforward. The unsigned integer, well, this is bit shifting 64 times and then subtracting 1, so that is this long number. If we added 1, this would wrap around to 0 or give us a compiler error. I don't know what Go does in this case, but in either case we wouldn't want to add 1 because it'd be outside of the scope of the unsigned int for 64 bits. And then we have this complex 128-bit number, and in case you didn't know how this math was done, we would square this number to get that. So 2 times 2 is 4, and then we're going to subtract 3 times 3, which is -9. So 4 minus 9 is -5. And then this number we get by doing 2 times 3, which is 6, and then doubling that to get 12. Example of a dynamic language. So Python is a great example of this. So here, as you can see, there's no type anywhere. And I'm saying let a equal 2, and then I'm going to print that value, which is 2. And then I'll say a equals the string hello, and then I'll print that out, and I get hello. Now, what are the advantages and disadvantages of these? Well, in my opinion, there's a lot more advantages of the static language because you know exactly what you should be assigning to a variable when it has a type. You cannot say assign to be the string hello because the compiler will yell at you because to be is a Boolean and a string is not a Boolean, and you probably don't want to pass a string into something that's expecting a Boolean because it will either be undefined behavior or just not compile at all. This also allows you to reason about the way the program works when you can see the type. So that is what I think is the most powerful thing about static languages, as the ability to reason the way everything should behave. Whereas in this, you could be assigning the wrong thing to a variable at a specific time, or somebody else, if you're collaborating on a code base, could be doing that. That's obviously not very good, and Python's not going to yell at you for reassigning A to a different type. Why is this useful then? Why would we ever have dynamic languages? Well, one thing that's nice is that if this is a short file, say anything up to 1,000 lines of code, what's really nice is that you could easily just scan the code to see if you made any of those errors. A very easy Control F. You will get crazy results if you did do something that expected something else. And dynamic languages are just that much faster when you don't have to type all this extra stuff out. So getting a proof of concept off the ground is really easy. That's the same with interpreted versus compiled languages. Compiled languages takes that extra bit of time to compile. Once it is compiled, though, it's a lot faster in the long run. Interpreted languages, though, you could just kind of start iteratively programming right out of the gate and getting your thing running as quick as possible. Some people care about memory access. I can't really show an example of garbage collection because it doesn't really translate well to a slideshow, but we could look at how memory access kind of looks. So what I have here is a file called address that's written in C. So we'll just pull that up real quick so you can see what's happening. For those that don't know, this is a pointer type, pointing to a type of int. And what that does is allow me to look into memory and assign addresses in RAM to a variable. And here I'm assigning just a regular old variable x, the value 9. Null means that this does not point to anything right now. Now what I'm doing is I'm assigning the pointer the address of where x is in memory. And then all I'm doing here is, here I'm printing x and where it's located. Here I'm printing the value of a, and then saying where a is. And then I'm also saying what is the value that a is pointing to something, and what is the value in that area that it's pointing to is this line. One thing you normally never want to do is increment a pointer unless you know that you've allocated memory for that, but I'll show in this example that in C you can do that. So what I'm doing is I'm incrementing the value stored in, or excuse me, I'm incrementing where A is pointing to. So I'm going to the next address in RAM. I'm going to print where A++ lives. Then I am going to print where it's pointing to, or excuse me, I got that backwards, but same thing. And then I'm going to print what that value it's pointing to is. So let's run this program. Okay, so we have the value x, which is 9. Great, does exactly what we want. This is a long string, but I'm just going to focus on the final 4 characters. So x is at the memory address 692C. Okay, the value of a is, well, this is again is an address, but look at that, 692C. Great, it's doing exactly what we wanted because I stored the address of x and a. The value of a is stored at this address, which is 6930, and the value inside of this address right here is 9, which makes sense because x was 9. Now I'm going to increment that pointer, so the value of a++ is, oh, well, 6930. That's kind of interesting. That's the same as this one. And that's kind of just a C optimizer thing, but it is kind of weird that it's putting these two right next to each other. The value of a++ is also at 6930, so that's kind of interesting. A is pointing to itself, but what's the value inside of A? Oh, well, 670525744. That doesn't really make sense. This is what's called garbage. So this is a completely meaningless number because nowhere in my code did I define what this memory address is holding. This normally won't work for too long. If I incremented this probably 2 more times, the program would crash because I'm going to be accessing part of the memory that the operating system won't let me access because I didn't define that I should be accessing that with an actual value. So that's called a seg fault. But C, for the most part, will let you do this in the beginning, which some people call C and C++ languages that allow you to shoot yourself in the foot. And some people like that. Some people like that they have control, and they don't like that languages like Java or Python take that away from them when they're designing stuff. But some people like the safety of Java and Python. So it just kind of depends what kind of person you are. And that's why memory access and garbage collection are interesting things to think about when choosing a language. Next, we have domains, libraries, and communities. So, since some languages are better suited for different tasks, despite having similar characteristics, it would make sense that some languages thrive in certain domains. So that's why I don't really like the general purpose idea of a language, because some things just are better in different languages, and the communities have really built off that. So in the video game industry, people like C++ and C#. This is Unreal Engine. This is Unity. These are both compiled languages. Lua is something that you could embed within these, but Lua is its own rich programming language. And then there's GameMaker Script, which is its own language, but you could only use it inside of GameMaker Studios. In the embedded world, which embedded is like Arduinos, or I think about it as any computer that doesn't look like a computer, so like a laptop or a desktop. That could be a pacemaker. That could be like your car's computer that's running all the stuff inside, like the governor for the gas pedal and stuff like that. And these are, this could also have been something called systems programming. They kind of go hand in hand, but that's these languages right here. The data science community is really dominated now by Python. It used to be pretty dominated by R. And then there's Julia, which also does a lot of data science, but each of these has their different pros and cons. And they're all in the data science realm. But I just wanted to talk about that history, which is why this asterisk is here. And then in web development, you obviously have things like JavaScript, TypeScript, PHP, Erlang, and Ruby. So kind of interesting. So I'm going to show some of this stuff along with some of the other stuff I was talking on this page as we move forward. So here is game code in C++. Now, not technically just raw C++. I am importing a graphics library called SFML, which I think it stands for Simple and Fast Media Library. Let me pull this up and go here. Yep, Simple and Fast Multimedia Library. So great way to start doing graphics. And let me close this. What we're doing is we're creating a window object here that's 200 by 200 with the title of SFML works. So as you can see, this is a browser and it has this title bar. Then I'm creating a circle that's 100 pixels radius, I believe. And then I am setting that circle to the color green. And then this is running code that as long as the window's open, so I don't have it on here because I don't have title bars the way they normally are in Windows or Mac, but you normally have the little X that you could click on to close a window, or the little red circle in Mac. That's what this is saying. As long as I didn't click on that button, then do all of this code. So we're gonna look for an event, and we're going to see if I hit that close thing, and then I'll close the window. Otherwise, I'm just going to draw this shape that I had up here and draw the window. So let's see that in action. So here I have this SFML app, just to show you that the code is the same. I believe this is game.cpp. Yep, so same exact code here, including SFML library and all that stuff. And then this is, I called it SFML app. So you could see green circle. The window is not 200 by 200 because I have a tiling window manager, so it's just stretching the screen to as big as it can fit. But if you're on Windows or Mac, or you were on a floating window manager, this would work exactly like you'd expect to be 200 by 200. And you can see SFML works is the title. So C++ is really, I don't want to say easy, but it's idiomatic to make game code in C++. This is embedded code. I might, at the very end, have a picture of what this looks like in the embedded Rust book, So you could see there's this LED matrix, and what is running is this code right here runs on this little matrix right here, and they don't have a video, but all it does is run around the perimeter of this and it glows. And you could do that in Rust. So one thing to note here is that Rust is a very memory safe language, but you could tell it, hey, don't tell me that I'm doing unsafe stuff because I don't want to hear it. I'm on an embedded system, which means I'm going to have to do some non-standard stuff that would normally be written on a normal computer. And then no standard library. I don't know what this no main does because we still have a main here. So I would have to look at what no main means here. I guess there's a not operator here and the not operator there, so I'm assuming that's what it's doing. But we have the X and Y coordinates, and one of these is forcing X and Y to increment, and then we're infinitely looping so that it goes around the LED. Now, some people think, why would you want an infinite loop? Well, think about a pacemaker again. That's going to be my standard example. I don't want that program to ever quit, so I'm probably going to have a while loop that is true at all times so that it just keeps running the code, because I don't want the pacemaker to stop. Same here. I don't want the LEDs to stop unless I basically pull the plug on the power. Compiler features. So some people like Rust because its compiler is kind of useful. So I have this program here called error.rs because that's a Rust file. And what it does is, you can see in this comment, fix the code to print hello world. So we should expect that print line exclamation point does not print hello world. But let's see what the compiler tells us. So we run the compiler like this. And it says error, cannot find the macro print ln, or excuse me, print line. I was skipping further. Now you do need this exclamation point because it is a macro. But the Rust compiler is kind of helpful here because it says a macro with a similar name exists and it's called println. So did you mean that? Well, we probably did. So we'd go into that code, switch it to println. And let's see. So it runs. And let's see if we have a binary. We do. Anything in green is a binary or something that I could run. Oh, look at that. So the Rust compiler actually helped us out here, and some people like that about Rust. It's a nice compiler feature that in this case was super simple, and C kind of does the same thing on some parts, but some of the errors in C or Java could get really esoteric. The Rust people have really gone out of their way to make the compiler try to be as helpful as possible and really give you niceties when errors do occur. Now, this doesn't necessarily fit in compiler features, but it's a language feature that's unique, so it fits in that unique category. And what it is in Java. So in Java, we have this. So we have a class, and you've probably seen this string array of args plenty of times. Well, what is that args? Well, we could actually see what it does. So I have this if else statement here, args length greater than 0. I'm going to print out whatever args 0 is. If not, I'm going to do hello world. So when I run this program, first I would have to compile it. Hello, and then I could run it. Okay, so hello world, nothing crazy there. But if I add a new parameter at the end of this and say people watching, hello people watching. So in Java, right from the beginning, you are forced to add this thing that allows you to interact with compiler options when the code is compiled down to the Java bytecode. And if you noticed here, let me pull up the addresses real quick. I didn't add anything here in main for C, but if you looked at the very beginning when we did C here, I did add, this is the equivalent in C. C just does not have strings, so you have to have a char star, which is the equivalent of a string, and then here, this is just telling you how many arguments there were. But kind of interesting that C and Java are languages right from the beginning that allow you to interact with that. Versus a language like Python, you actually have to import a library called OS, and the OS library has a function for command line arguments. So kind of interesting. A lower level language has the feature built in, and the higher language level doesn't. So let's see. We were here, so we just went over that. Both Rust and Java kind of have unique things built into them. Data science, so this is an example in R. So Plotly is a library, but it's very easy to get in R. And what we're doing is we're making a figure, and that figure is a histogram based off different categories of sugar levels in different cereals. So if I go to the next page, we could see what that produces. That's this nice histogram. One big reveal when I first did this is that the this whole slideshow is actually written in R, which I'll show the source code at the end and upload it to the Discord page. But we could interact with this graph, so we could see the different values here. And we're going to go like that, and we could see that we could lasso them and select different values, so that's kind of cool. And we can compare all the different values. So really easy to do in R, because R was built for data science. It was built for statistics. So it's cool that it has all this stuff, not necessarily baked in, but it's very easy to do with the tools that are idiomatic to use in R. You can build histograms in just plain old R, but this is kind of a nice feature. So Unicode support, so slideshow doesn't, the slideshow itself does not support Unicode, so, but I have the slide up to remind me what to type. So I am going to launch the Julia REPL, which is what this is. And if I type that same thing, var epsilon, don't want to spell it wrong, and then I hit the tab key, I get the symbol epsilon there, and I could set it equal to a value. So since it's epsilon, it only makes sense that we assign it a pretty small value. And then what we could do is we can, obviously you wouldn't want to type this all out, which you have to in a REPL, but when you're generating the code doc, sometimes it's just nice to look at a symbol versus a long name. And we could do the same old math we could normally do on any variable, times 2. And we could see that we doubled that variable. So some people really like that there's Unicode support directly built into Julia. So you could also set emojis equal to stuff, which is kind of nice. JavaScript obviously dominates the web. So in Brave, we could do Control-Shift-I to bring up the developer tools. That might be different in Firefox or Chrome. I don't think so though. But let's change the color of this box right here by doing this. So just going to type in document.get document, wow, I cannot spell today, .get element by ID, and we're going to do the choose me. Don't worry if you don't understand this. Hopefully there will be a talk about web design in the near future. And we're going to set that background color equal to, this one is FF0000, which is red. Here I have 0000FF, which that is blue. So we expect expect the background color to be blue when I do this. And look at that, it is. Let's make it that red. So obviously this is now a little bit harder to read. Well, let's change that. So in JavaScript, I'll take out the background part, and you would think it'd be foreground color, but it's actually just color, and it's lowercase this time. And let's make that white, which is FFFFFF. And look at that. And then we could change the size here with the second line. JavaScript makes you put everything in strings, so I put 20 px there, but I actually know that's pretty small, so let's do 80 px. Oh, and let's see, oh, because it is not size, it is font size. Cool, so we've just now interacted with JavaScript. Since JavaScript is a scripting language, you could actually play with it in real time in your console. You could actually go to any website. So one easy one to go to is example.com. And if I launch the browser tools, I could actually do the same thing here. But this time I'll have to do by tag name. And we want, let's do the H1 tag. And let's see, so there is an H1 here, so kind of nice. That's in an array though, so we have to grab the first one, and then I'm going to change this to green, and let's see if example domain here, which is the header one. Oh, look at that, it changed to green. So you could do this on any website, you don't have to own it, and it doesn't have to be on your computer. Obviously it doesn't change it for everybody, you just hit refresh, but kind of cool. Oddity, so things you have to be careful about in any language, but I chose C in this example. So I have a program here called weird.c, and all we're doing here is just some standard old math. So 200 times 300 times 400 is the first one, and we print the result, and then all we're doing is tacking on 500 to that. That's the first pair. So this is going to be a pretty big number, and this should be an even bigger number. Both of these are positives because there's no negatives. And then here we have 3.14 plus 1 to the 20th power, or excuse me, 1 with 20 zeros after it, minus 1 with 20 zeros after it. So these are huge numbers, and this is a relatively small number. And then this is the same thing, except now I've just changed the associative property of it, which should work because the minus sign is over here. If it was in here, that's a different story, but this is addition and this is addition, so nothing should change. But let's see what happens when we run this program. I already have it pre-compiled. So 200 times 300 times 400, so 3 times 2 is 6, times 4 is 24, with a bunch of zeros at the end, so that makes sense. But when I add 500 here, I get a negative number, so what's going on there? Likewise with the 3.14 plus 1 with 20 zeros, well, that equals 0. That's kind of interesting because this and this should just cancel out. Which in this case they do. So why are these seemingly the same operation if I didn't include any parentheses that should still work to be this one? What's going on here? Well, in this case, integers can only have up to, I believe, 8 bits of information, or 4 bits, I can't remember. So an int isn't big enough to store this times 500. So it's wrapping around into the negative region. And in this case, I'm getting underflow kind of. And so things are just kind of not working out. And this could happen in any language, is the oddity. So sometimes you have to be looking out for that. And C, all you would be doing here is changing the type of this. This is a little bit more tricky to deal with because you would have to either get a longer type, like a long double or something like that. So it could be a type issue. There's other ways to get around that, but to show you that this isn't just a C problem, if I pull up that good old JavaScript console here and I do 0.1 plus 0.2, oh, look at that, 3 point, a bunch of zeros and 4. What's going on there? Well, 0.3 you can't just kind of represent in a computer. So when it does the 2 to the power of negative values, this is the kind of closest it could get to 0.3 in an accurate way. So just be on the lookout for this in any language. This has to do with the IEEE standard for floating point numbers, but it's not something that people think about because different languages sometimes get around this, but not all. So it's really nice to look out for these in languages and learn sort of the gotchas in them. The last time I gave this talk, my hard drive failed. That didn't happen this time. I was just a little lazy. But it is nice to just go straight to the internet and see what's going on. So I am just going to go here and let's go to Haskell's website. So let's go to the home page. So on Haskell, if we scroll down just a little bit, we could see testimonials right here. So you should know that all of these companies right here use Haskell. They use it in their production code, and these companies probably make millions upon millions of dollars. And if you want a job at one of these places, or you think that their testimonial is good, maybe you want to use Haskell. You could also look in the sponsor section of different languages, so sometimes that's nice. Let's look at Zig, which is ziglang.org. So if I go down here, we could see Tiger Beetle, Blacksmith, ZML, Bun, which if you know Node.js, Bun is an alternative to that. Bun is written in Zig. Most of these are people, but you could look at where these people work and probably know that they use Zig. So these are really nice ways to find the companies that care enough about a language to actually sponsor and tell them that they like their languages, give them lots of money to develop their language. You could kind of do the reverse. Before I do that, let's go to Python, because Python is actually nice because they have success stories, which are just a bunch of testimonials in specific domains. But Python also has a job board, and these people are specifically hiring developers for Python. And you could see they have a job board sponsorship, so all of these companies use Python as well, which is kind of nice. Now, this website is not updated a whole bunch, but sometimes it's nice to look here and kind of do the reverse. You could research a company and look at their tech stack. So let's just browse here and see. Let's look at what Pinterest is doing. So Pinterest, I know, is written in Python, but let's see what their tech stack is made up of. Oh, why is it going so far back? Oh, so these people are actually showing kind of the flow of where their architecture is going, but I wanted to see the language stack. Here it is. So they use Python, they use MySQL, they use PostgreSQL, they use Redis, which is another database. So lots of databases here, probably for different reasons. They're still using R, and they use Jupyter Notebook. So remember, that's Julia, Python, and R. So kind of interesting that they use all these tools for Pinterest. Let's look at another company real quick. Let's look at Uber. So you could already see they're using Python, and I believe that's React, or no, it's jQuery, excuse me, Node.js, Java. So kind of cool. You could see all these things that these companies use. Like I said, it's not super up to date because I know Uber is using Zig. There's a big talk on it and why Zig was important to new features in Uber, but you could still at least look at what they were using and be like, oh, hey, Uber doesn't sound like a bad company to work for. Maybe I should learn Python and Mongo and figure out how to work with them together. And that's obviously a big reason in general. So I know, let's see, I think OCaml I know is specifically used for Jane Street, which is a financial tech company, and you could see all of these places actually use OCaml. So kind of cool. If you go to Jane Street's website, I think they tell you that they use OCaml as well. So probably a really cool language to pick up, right? Because lots of you are looking for jobs. So it's cool to look at the companies that you might someday be interested in working for and just research what they actually use. So that's the end of this talk. Feel free to ask any questions in the Discord. This is not the full credits, but I do have a file that I'm going to upload along with this to include some of the other stuff and where I got it and how you could start exploring these languages if they don't already have a way to explore. So here, OCaml has a playground. Haskell also has a playground right in here. So you could start playing around with them on sites. Some OSs come pre-installed with languages, so Linux comes pre-installed with Python. But that will be in that note, that text file that I'll upload to the Discord. But thank you all for watching. And again, please ask any questions if you're interested, and hopefully we could have a discussion. Thanks all, and have a wonderful day.